So when I was a kid, I used to play the guitar. I wasn't amazing, but I wasn't the worst either. Yeah, when I started university, it just faded away. I stopped working on it 10 years later, and I've decided to pick it up again. And needless to say, I am definitely out of practice. I have a long road ahead of me, but I decided to make myself feel a little bit better by, instead of working on something that I am not that well versed in, I will work on something that I am very confident and very well versed in, which is to make something for it. And this is what this video is about. But then I decided that since this would be too easy to just do, I would use this opportunity to learn something that I've always wanted to add to my arsenal, and that is topology optimization. Back in undergrad, I studied this as a pen and paper method. These days, I'm proud to say that I'm much better at finding the easiest possible way to solve a problem I admittedly caused myself. In short, topology optimization is a design method that converts whatever part you are studying into a series of... Actually, you know what? I'm going to draw it. So you can see here, I'm going to draw a very simple part. In this case, it's a crane hook. Now you can see that this is kind of the side profile of the part. Now, let's say for example that you want to run topology optimization on this part. First step, you're going to need to do something called a finite element analysis. What that means is that you convert this part into very tiny blocks, for example. And each one of these blocks represents a section of it. And it's a cube, it's in 3D. It has 6 sides, it has 8 corners, and it's connected to other blocks or the air. You can imagine that each one of these blocks has a sensor, each one of its corners or its sides. And when it's connected to another block, we measure how strong or how much force each connection from one block to the other is put under. If you want, you can make these blocks smaller. What that does is, let's say for example, we have a hole like the one on the top here. If the block is too big to represent what that hole does, making the block smaller means that all the very tiny features that make up this part are now represented more accurately. And that's helpful. But in engineering, usually there's always a trade-off. And in this case, the trade-off is that when you have more blocks, you have more blocks. Let's say, for example, you have all of these blocks. Suddenly, that's an 8x multiple of the number of blocks you have. So that's really the trade-off with finite element analysis. Now, after you do a finite element analysis, what you have is a 3D heat map of how much stress or how much each small element of this part is carrying. That's what the name finite element analysis is comprised of. When you say finite, you mean a certain amount of power. Turn this seamless part, basically just because it's much easier to calculate stresses on a cube. So when you turn everything into a square or a cube, it's just much easier. The methodology of topology optimization tells us, hey, listen, let's optimize the amount of material and let's make sure that whatever is there is optimized so that it's what's carrying the load. And whatever isn't carrying the load doesn't need to be there. One of the very famous examples of topology optimization is an I-beam. Let me show you. So an I-beam is one of these really famous examples engineers use to explain optimizing for materials, basically. Because listen, steel isn't free. You have to pay for this part, and you also have to pay for transportation to carry it. When I'm bending something, the stress isn't the same across the entire cross section. If we cut down the middle, what we're going to see is a lot of compression, pressing on the top, and a lot of tension at the bottom, or vice versa. So let's say, for example, I'm bending it this way. This top part, all the very tiny blocks that we can imagine are going to be pulling away from each other. And on the bottom, they're all going to be pushing into each other. We can see in this diagram what it looks like. And the maximum amount of pulling is at the very, very top, and the maximum amount of pushing is at the very, very bottom. So from that, we can determine that where the material really needs to be is at the top and the bottom. And we just need some material in the middle to connect them both together. And that's how we come up with the very, very obvious and very, very recognizable profile of the I-beam. That's actually why it's called that, because we decided to put all the steel where it matters the most. We get the most bang for our buck. So now we have a better idea of what topology optimization is. I'm going to talk about what I want to do with it. So now that I have a guitar, I want a place to store it. And right now it's just on the corner on my floor. I don't like that. I recently moved into a new apartment. I'm very, very happy with it, but I've been hanging things left and right. And I figured, why don't I just hang my guitar? Thing is, guitars are heavy and expensive, and so is the floor. So number one, I don't want the guitar falling, because then I have to get a new guitar or fix this one. Number two, I don't want the guitar falling because it has to fall somewhere, and the floor is heavy and expensive, and I don't want to fix that either. Number three, I wanted to make a video because I haven't really released something in a while, and I felt this need to kind of talk about topology optimization. I figured this would be a really good excuse to do something that I've been wanting to do for like 10 years. So now you have to watch me do this. Now I'm lucky enough to be experienced in a software that actually has a topology optimization module in it. SolidWorks. I learned it in undergrad. And so let's walk through the design process of how I iterated it. So this is by no means a tutorial on topology optimization, but I wanted to go through my design process because while it isn't strictly an optimization-driven approach, I do use topology optimization to refine and validate my design, and I rely on it heavily throughout the entire process. I started out by designing the part myself, just based on what I think would make the strongest shape. Obviously, it was a bracket in the beginning, but I also wanted to accommodate the curvature of the guitar, how it's going to be hanging, all of these different, details. Next, I whip out the design study toolbox and define some key things. First are the loads. I need to tell the program what areas are going to be carrying the guitar and what direction the guitar will fall towards, pretty much where gravity is. Next are the fixed points. I always have to remind myself that the software doesn't know anything, and I have to teach it everything from the beginning. Once you have to define the direction of gravity, you pretty much just assume that you're talking to a set of equations, and you really, really have to define everything. This is the thing with software and algorithms. It's great because they do exactly what you tell them to, but it sucks because they do exactly what you tell them to, not what you want them to do. Anyway, next are the fixed points. I plan on attaching this part to the wall, and that's what these holes are for. I need the program to know this, and I do that by defining these areas as fixtures. I'm probably just going to screw them into the drywall, but that's something that I get to decide, not the software. Now, SolidWorks, as well as a few other CAD programs, use faces to identify these definitions. So when I was designing, I actually had to go back for this. I made sure that there were separate faces when I was designing the part that I knew would be holding the guitar. So any interfaces where the guitar will be touching or I'd be screwing something in, I could define them there so that I could actually pick them out easily and identify them later on and attach them to certain things like load bearing or fixtures. Finally, I had to define the objective. In my case, and this is kind of the default with topology optimization, it's finding the highest stiffness to weight ratio. Now, I don't know if you can look around for this, but you can actually see topology optimization everywhere you go. Things like angle iron, things like those cool web thingies, shelf brackets, all of these things are forms of topology optimization. After picking the material, which in this case isn't important because I'll explain why later, it's based on actually I can explain it now. I want to identify the high stress points qualitatively. I just want to see where the material is going to be under a lot of stress. I don't need to know what the numbers are. So the material itself doesn't really matter as long as the material doesn't matter. Let's put it that way. After that, I picked the mesh size, and the mesh size, this is a very important term. It's one of the most important terms with, I think, finite element analysis in general. Remember the Legos from before? The mesh size is what defines how small these Legos are. These small Lego cubes are. And I talked about the trade-off. So in this case, this is the real-life definition of it. I want the smallest possible size so that it captures all the information, but I don't want my computer to crash and possibly melt parts of it away. So my approach was to find the smallest geometry feature that I cared about in the part itself, and then make sure that it was represented in the mesh by defining the mesh size that way. Luckily, SolidWorks shows a mesh overlay, which you can see here, and it helped me do exactly that. Next, there's really not much to do but run the study. And this is what I get. So while this looks pretty, it tells me two things. It's really all I need to know. Where I can remove the material and where I can't touch the material at all. That's really all I care about. So I take this information and I go back to my part design, remove where it's blue, keep where it's red, and then head back to the design study and validate that I didn't compromise the structural integrity of the part. And after doing this a few times, I end up with this. This is the first iteration. I actually like it a lot. I love the texture I have. It's super, super, super stiff. This, by the way, this is PLA. It is stiff, man. It is very, 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 it's not going anywhere. Intuitively speaking, when I look at this, I think to myself, yeah, obviously there doesn't need to be material here. You don't need material here. But it's really, really nice that this is a validated, like research, like analytical approach. This is my favorite type of math. The type where I don't have to work things out and I still get the results that I want. I thought this would be the final part. I even have footage of me hanging it, but the problem is that I was testing it out and it turns out that the curvature here is an issue. So when I hang the guitar, what I have is no issue with it going back and forth, and that's a problem. Also, this is very smooth and the layer lines show. I don't know if you can see. You can definitely see. Yeah, the layer lines show, and I don't like that at all. So after going back to the drawing board, I was done with this and made this. I figured out that this texture, it's a fuzzy skin texture. She does a pretty good job of hiding the layer lines. I mean, I like a rough texture. It's a bit stringy, to be honest with you, but a butane torch will just take care of that in 2 seconds. I'll tell you what, I ironed this flat top and it shows. It doesn't look that 3D printed. It's pretty good. Even though I added these, this is my solution. It's the indents here. If you want to hang the guitar, so if I have my guitar here, it's slightly too narrow. So this final width here is slightly too narrow for the neck. You try and put it in, but it doesn't work. It doesn't fit because this is slightly smaller than the neck. So what you have to do is put it in diagonally like this. And that's the whole thing. That's what keeps it in place. The big issue is that since you have a completely flat top here, then it leaves room. It puts all the pressure on this area. So this is something that I wanted topology optimization to kind of fix for me, but this isn't something that you can fix with topology optimization. One thing I learned, which is I think one of the more important lessons, is that I've said this before and I'm gonna keep on saying it. You can't know everything until you test. You have to test your products. And this is why testing is so important, because the reality of the situation is that sometimes you just can't simulate life. The whole point of the simulation is that it's not life. It has to be rudimentary enough for it to give you an answer, but not complex enough for it to just be the real world. That's the whole point of models. At this point, I'm pretty much at the refinement stage of the product. All I did was add a detent here, carve this out, and then a bit, come with like a V, and then I just hung it. So the moment of truth, I've done this, this isn't the first time I do it, but I just want all of you to see it is holding on to it. It looks great. I'm very, very happy with this. And what I was talking about with the angle is that there's a push part here that prevents it from pushing out this way. So yeah, that's it. I'm very happy with the way this turned out. I have these to show for it. I learned a new skill, this topology optimization. And to be completely honest, this is something that I'm going to use a lot more often. I think it's a very powerful tool. And I think for how easy it is to kind of implement, even in a rough rudimentary way where I'm just iterating and I'm seeing roughly how things are, it's I think it's worthwhile to learn. I recommend anyone who wants to design products that are load bearing, that get under stress, to learn it. And just one word of caution, this is by no means a tutorial. So anyway, thanks for watching. And yeah, I'll see you in the next video.